So last time we had met, I'd asked you guys to look at section 2.1 and then to work on a couple of the homework problems. So I'm going to start with questions from that. In general, how'd that go? Fine-ish. So start with questions from 2.1 if anybody has any. And then we'll just keep on moving. Sure.
Can you do 8?
8?
Part A.
Yeah, sure. Okay. I'm going to do this on the calculator. So again, for calculus, we'll probably need to be in radian mode. I'm going to start by going to the y equals menu, and I'm going to input my function here. We'll use x's instead of t's. Hopefully nobody's surprised by that. Okay, so far so good. And the average velocity is just a slope. So I'm going to do y2. So I'm going to use a function notation to kind of have the calculator plug the number in for me so I don't have to plug in every time myself. So to do that, I'm going to press vars, go to y vars, pick function, and then pick y1. So I'll do y1 of 1 minus y1 of 2. So again, go do the same thing. And then the change in x's is 1 minus 2. So there's my first one. And now I'm going to just change this now. All the 2's I'm going to turn into 1.1's. So I'll just press second and enter to recall the same thing and just update that because it's like way less button pushing. There's my next one. And we'll do 01. And then 001. So that's that. So if I'm looking at the sequence of numbers, we go from 6 to negative 4.7 to negative 613 to negative 626. Looks like we're heading to maybe negative 2 pi. That would be my guess, looking at that sequence of numbers. Is that okay with you?
Yeah.
Do you like this little calculator trick of how I did that so neatly and quickly with my calculator?
Yeah.
Like, that's a good one. Like, whenever you're asked to do, like, a whole series of calculations that are basically the same, like, I'm not plugging that in over and over and over again. I'm just going to set it up once on my calculator and do the update. That feels, to me, much easier.
Mm-hmm.
Cool?
Yeah, thank you.
Of course. Any other takers here from the homeworks? They're all kind of the same problem over and over again, right? I think there's just 4 problems. Yeah, I think that sounds right. There wasn't much to this section. Okay. Let's start 2.7 then today. So 2.7, we're going to be introduced to the concept of a derivative and talk some more about rates of change. Remember, velocity is an example of a rate of change, as is slope. Okay, so we'll start off with the same idea that we had talked about in 2.1. So how do we find the tangent of a curve at point P? Well, we need slope and a point. To come up with that slope, we start with a secant. So we pick some point Q, also on the point f of x, and we look at what's going to happen as that Q gets closer and closer and closer to P, right? And when Q and P are the same point, that secant has become a tangent. Everybody's okay with that? So just like before, we start with the slope of the secant line, so that would be y2 minus y1 over x2 minus x1, or change in y over change in x. And if we get Q closer and closer, as we notice, we start off with like PQ, where Q is down here. Each time we move it, that slope is changing and getting closer and closer to the slope of that tangent line. So the way we represent that is with a limit. So we'll start with this definition. We say the tangent line to the curve y equal f of x at the point P, a comma f of a, is the line through P with slope. The limit as x approaches a of f of x minus f of a over x minus a, provided that the limit exists. Same idea that we saw in 2.1, right? That instantaneous rate of change was the same as like taking a secant line and getting those points closer and closer and closer together till they're the same point. Or, more common way of representing this is with the formula limit as h approaches 0 of f of a plus h minus f of a over h. Now this is the same formula as this one. We just define things a little differently, but it represents the exact same idea. Let's look at a picture and kind of explain to you how the formula is the same. Sound good? So here's my point P, a comma f of a. Here's my point Q at the x-coordinate x or a plus h, and the y-coordinate f of a plus h. So we've just moved some h units to the right, and as that movement to the right becomes 0, Q and P become the same point, right? So if I do y2 f of a plus h minus y1 f of a over x2 a plus h minus x1 a, so that a plus h minus a becomes just h. This is kind of becomes the more standard way of representing this slope of the tangent line. The reason why we tend to prefer this representation over the other one is because here the a could be any number, right? But with this representation, the limit is always h going to 0. Every time you write a tangent line, it's always going to be the same kind of limit, h going to 0, as opposed to this one where the a will be different in each case. So typically we end up with this. Could you use either one and get the same answer? Yes. Would there be situations where this representation might be more useful than this one? Possibly. If there's some weird kind of factoring trick or something you might need to pull where it's easier to deal with it here than here. I think I've seen one before where this definitely becomes more helpful, where you have to like factor a perfect cube or something. Or a difference of two cubes, I should say. But in general, it doesn't really matter. Everybody still is doing okay? All right, let's look at an example. So find an equation to the tangent line of the parabola y equals x squared at the point P, 1, 1. Okay, so it doesn't matter which representation we use. I'm going to choose to use this one as it's the more standard representation. Everybody so far so good? Okay, what does f of a plus h mean? So it's me plugging in a plus h into x squared. So that would be a plus h squared. Everybody's okay with that? What's f of a going to be? A squared all over h. Just real quick before, why am I bothering to do this? What about what's going on with the first limit that I'm continuing? I just didn't even bother trying to evaluate it right there.
0 at the bottom.
If I did a direct substitution, I would get 0 over 0, right? So nothing to do with, not anything I can do there, direct substitution. I got to grind here a little bit and hope that that works itself out. Okay. If I FOIL out a plus h squared, I get a squared plus 2ah plus plus h squared. And I still have the minus a squared, and we're still all over h. What do you notice? A squareds cancel out. Anything else?
Factor h.
Yeah, I can reduce out an h, right? I'm going to just do it that way rather than showing the factoring and then reducing. I'm just going to reduce an h out of everything. Well, that's really lovely. So what do we have left then? We just have 2a plus h. Can I do the limit now? Yeah. How would I do it? Yeah, just direct substitution, so just plugging 0 in for h. So that's my slope. What is the a in this case, though? 1, right? So if I want to write my equation for my line, I'm going to use the point slope formula because that's what I'm given is a point and a slope. So y minus 1 equals 2 times x minus 1. Could I change that and write it in slope-intercept form if I wanted to? Sure. In the back of the book probably does. I don't care, personally. Chanel.
So how do you decide which value is the a value?
Always the x.
Okay.
Remember, it's always a comma f of a. So the x is always the a. How was that? It's okay?
Is that your final answer then?
Yep. What I boxed up there in the green is my equation of the tangent line. Because I already had the point, 1, 1. I needed the slope. That was the limit part. Once I had a point and a slope, just plug them into the point slope and I'm done. Let's do another. So again, tangent line. So I need a slope and a point. So just start with my generic formula. Again, I notice if I do direct substitution, that's always just going to be 0 over 0 at that point. So I know I got to do stuff. What is f of a plus h going to be?
A plus h over 3.
You mean the other way around? 3 over a plus h. Remember that y is my f of x. Okay, and what is f of a going to be?
3 over a.
3 over a. Okay, what should I do next?
Common denominator.
You could do that. This is the way I prefer to do it, that avoids having to make a common denominator, is I'm going to multiply the top and bottom by a times a plus h. So when I multiply it, a times a plus h to 3 over a plus h, what am I left with?
3a.
3a. When I multiply it to negative 3 over a, what do I get? And the denominator, I have that. That, I think, is a little bit easier than making common denominator than multiplying by the reciprocal. Although that's still correct, you can do that. It's probably not much shorter, but like that I can basically do in my head. Making a common denominator and multiplying by the reciprocal, I can't do that in my head. It's just too much to hold. But that I can. Well, let's distribute things through now, because we still haven't really canceled anything, right? Oops. What do you notice?
3a.
Yep. And what else?
H.
Reduce out the h. Everybody good? So when I evaluate the limit, what's that going to equal?
Wait, where did the a go? In the denominator?
Oh, sorry, excuse me. Thanks. And what is my a in this case? So that's my slope. So y minus y1 equals m times x minus x1. And I should be good. Everybody still feel good? Okay. For physics, remember that average velocity is just displacement over time. If f is my position function, that displacement over time would be f of a plus h minus f of a over x plus h minus x. I'm sorry, a plus h minus a, or just reduces down to this. So the instantaneous velocity is just going to be when h goes to 0, which again is the same as the slope of our tangent line, right? So the instantaneous velocity would be the same as the slope as the slope of the tangent line for our position function. Oh, righteous. It's all the same thing. Sweet. Okay. Let's look at an example. Suppose a ball is dropped from the upper observation deck of the CN Tower, 450 feet above the ground. What is the velocity of the ball after 5 seconds? Physics students. One-dimensional motion. What's my equation? There you go, 1/2 AT squared. So notation for everybody, S is the traditional letter we use to describe displacement or position. V for velocity, A for acceleration. Now, what is acceleration if we're dropping something?
Negative.
Well, it's just going to be gravity, 9.8. I'm just going to call it positive. It doesn't really matter whether it's negative or positive in this particular problem. I'm just going to worry about it just making it positive. right? Everything, if you're just dropping straight down 450, accelerating at 9.8, or if you're going straight up with an acceleration of 9.8 to 450, it's all going to be the same, you know, if you're ignoring gravity. So it's whatever. So there's my position. So that's my function, right? So my v of a is going to be s, or the limit as h approaches 0 of s of a plus h minus s of a over h. So far, so good. Same idea as before. What is s of a plus h? Just 4.9 a plus h squared. And then s of a is just going to be 4.9 a squared. Still feeling good? If I'm going too fast, stop me and it will slow down. Or if you're missing the detail, like stop me and we can, you know, say more. If you feel okay, then we'll keep going. I'm going to FOIL that out and then distribute the 4.9 through. What do you notice?
0.9 a squared.
And
H.
it's like it's the same reducing every time almost, doesn't it?
Yeah.
Yeah, it's lovely, isn't it? When like they all kind of feel the same. Oops. Put that a little bit more squarely there. So far, so good. So v of 5 is going to be 9.8 times 5. And what's that come out to? Oh, 49. That's meters per second. Still doing pretty good. Okay. Part B says, how fast is the ball traveling when it hits the ground? Well, the first thing I want to need to know is the time when it hits the ground, right?
Yeah.
So how can I solve that?
Set y for 0.
Well, I'm going to think about it as, I'm going to use the position function to do this, right? Because the position function is describing the position. So on the ground would be when it's traveled 450 meters. So I'll divide by 4.9 and then square root both sides. And I'm going to drop the plus or minus because we're talking about time, right? So that's about 9.6 seconds when I dump that into my calculator. So what would the velocity be then?
4.9 times 9.6 squared. No.
Just 9.6, v of 9.6.
Oh.
Right? So just plug it back into that velocity function that we got from before, right? So I'm just using this. where A is 9.6.
So the position and velocity equation is the same.
No, so the position function, S of t, is 4.9 t squared. V of t would be 9.8 t.
Yeah.
Right? So they're different functions. But the t, the time when the position is 0 will give you the velocity when the position is 0, right? So far, so good? Okay. Vocab. The derivative of a function f at a number a denoted f prime of a So when we write this symbol, that's read as f prime of a. That's the derivative of f at a. Is, well, isn't that just the slope of the tangent line? Or the instantaneous velocity? Oh, it's all the same thing. Yeah. So when we talk about the slope of the tangent line, the derivative, instantaneous velocity, all of these things mean the same thing. It's the same process to find them. They all kind of mean the same thing. Cool. All right. And notice here I give you two definitions, right? This one was the same as this one, or even this one. And notice this slope of the tangent line definition is the same as my alternative derivative definition, right? You guys see that? They're just still the same formulas. Cool beans, dude. So if we want to find the derivative of the function f of x equal x squared minus 8x plus 9 at the number a, so we're looking for f prime of a. Well, that's just the limit as h approaches 0 of f of a plus h minus f of a over h. Well, Mr. Kulik, it's all the same? I mean, basically, dude. What is f of a plus h?
A plus h squared minus 8 times a plus h plus 9.
Mm-hmm. And then what's f of a?
A squared minus 8a plus 9.
Okay. Does that look good to everybody? Nobody objects? You're wrong! Oh no. I really thought that was right, Mr. Kulik. Now it's right. I do that because this is such a common mistake. I want to make sure I yell at you and get your attention so you see how easy it is to make the common mistake. You were all fooled when I wrote it down and nobody objected. Make sure you're being careful. Okay? That negative sign needs to distribute to the entire f of a. This is me warning you. All right, let's FOIL some stuff out. What?
Is it minus 9? Isn't it minus?
Oh, yes, thank you. There we go. Yeah, if you see a mistake, just yell at me like, Don't let me go far. You did a good job. I didn't even get to write the next thing before you're on it. Girls, we good? Okay, I'm just checking. If you have questions, stop me and ask. Or if you just need a minute to process, because like Mr. Kulik, you wrote down a whole boatload of stuff and I'm still writing and not having a chance to think yet. It's okay to be like, give me 30. No biggie. We have the time. What do you notice?
A lot of stuff.
A lot of stuff can cancel. Let's look. I see a squared and minus a squared. I see a minus 8a and a positive 8a, a positive 9 and a negative 9. Everything left, you notice now has a factor of h. So we can reduce that stuff. And now I can do the limit, right? Just by direct subbing. And we're done. So that's my f prime of a. Everybody's cool? So the tangent line to f of x at the point a comma f of a is the line through a comma f of a whose slope is equal to the derivative of f evaluated at a. That the slope of the tangent line is equivalent to the derivative at that point. Cool? That's our big takeaway. So if I wanted to find the equation of the tangent line to that same parabola we just looked at through the point 3, negative 6, the slope of that tangent line is just going to be f prime of 3, right? Because my parabola here is the same as my f of x from before, I can just use the derivative from the previous example. Oops. And I'm done. And again, I was able to use the derivative from the previous example because the function in question was the same, right? So far, so good? Okay. So the other thing that we talked about in 2.1, other than just like position velocity, we talked about just like rate of change in general, right? So remember, if I have some rate of change in y over change in x, that's just the slope, right? F of x2 minus f of x1 over x2 minus x1. If I want the instantaneous rate of change, that's going to be the same idea, but it's going to be the limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. What does this look like?
Slow.
Doesn't it just look like
Y.
this? Just x, or a is x1, x is x2 and a is x1? Isn't it just a derivative again? Instantaneous rate of change is just a derivative. Oh, it's all the same thing, Mr. Kulik? Yeah, dude. Yeah. Instantaneous rate of change. Slope of the tangent line. Derivative. Instantaneous velocity. all talking about the same process, doing the exact same thing. Cool. All right. So let's look at this last couple of examples here. It says a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is C equals F of X dollars. What is the meaning of the derivative F prime of X? What are its units? What does, in the context of this problem, what does F prime of X mean? So if you're asked this question, it needs to start. It's the instantaneous rate of change of what quantity?
Cost of fabric.
Of C, right? That was our cost of fabric, yep. With respect to, so this is your dependent variable, right?
Oh, the yard of fabric. X.
With respect to X, yep, that's your independent variable. Or, in other words, the instantaneous rate of change of cost of production with respect to yards of fabric produced. Oops, forgot to say fabric. So our unit here would be dollars per yard. Is everybody okay with that? Did you like how I did kind of in general, where it's like it's always kind of formatted this way? Instantaneous rate of change of or dependent variable with respect to independent variable. And then you can like fill in the context for the specific problem. Okay. In practical terms, what does it mean to say F prime of 1,000 equals 9?
Cost of 1,000 yards of fabric is $9.
Not quite. So you'd say when producing 9,000 yards of fabric, it costs $9 per yard to produce that fabric. So that's the cost of production when you're making 9,000 yards of fabric. From our basic economics, what do we know about cost of production?
The higher the cost of production, lower the supply.
I'm talking, okay, with regard to like amount of product produced.
Less can be produced.
As production goes up, cost should go down, except in what instance? Where you exceed your limits of production. So you might have to build a new factory all of a sudden, so you incur a bunch of new cost, but then production costs should go long-term, continue to go down, right? Yes, no.
It's 1,000 yards, right? 9,000.
Oh, yes. Sorry. Absolutely. It costs. Grammar is hard, guys. Which do you think is greater? F prime of 50 or F prime of 500?
That's probably
Yeah. And the reasoning being that as production goes up, cost of production should go down, right? They then ask, what about f prime of 5,000? And I would say, assuming the limits of production are not exceeded, f prime of 50 should be greater than f prime of 500, which should be greater than f prime of 5,000. But that's, again, making an assumption that you don't violate your limits of production, right? That type of quantity increase, you very well might need a second factory or something, you know. In which case, I would not be surprised then if all of a sudden it's more expensive to make your 5,000 than it was to make your 500. But by the time you got to near the limits of production, you should be producing for less than the 500 was. All right. Yeah, I don't want to do this right now. Get rid of it. Okay. Oopsie daisy. I don't have those highlighted there. Let me grab them from second hour because I know I had them highlighted there. Okay. So, homework for 2-7. We got some boldies in there. What's that mean? Homework quiz. So we should expect to see that next time. What's the takeaway, though? Everything is kind of the same, right? It's all just doing the same limit thing over and over and over again. So that's it for 2-7. So my assumption is this next section of, or next set of chapter or sections that we're going to do before the next test should be considerably easier than the last test. The things we're going to be doing here are massively less theoretical. It's mostly just like symbol pushing, which I think is much closer to our comfort level for a mathematics class. And I would say the same thing as for the following test is, again, going to be a lot of symbol push. The next test after that will be harder because it gets a little bit more application driven, which is a little bit more like less, or it becomes a little less systematic. You have to use a little bit more creativity and like thinking about what's going on, which is, I think, the hardest part of all mathematics, not just for us, but I think for any mathematics student, that's the stuff that's hard. And then I think after that, we have another easy test or two, so I think that'll be kind of how this will go, because the theoretical stuff kind of backs off or becomes more intuitive, the theoretical things. It's not quite as abstract as the limit was, and like having all these different contexts and, derivative of a piece, having all these piecewise functions rattling around and having to think about limits of this and like, when can I do the substitution, when can't I? That stuff all kind of takes a back seat for a little while, and kind of is running in the background. So I think that these next test or two should be considerably easier than the first one. It's just kind of the way it has to work, as we lay that theoretical groundwork, and then we can do these specific things and kind of move out of the theoretical arena and into like a very specific arena, which I think we'll be more comfortable at. Chanel?
So is this next test only on 2.1, 2.7, 2.8?
No. So if you look from test 1 to test 2, we have 2.1, 2.7, 2.8, and 3.1 and 3.2.
Oh, so it's like the last chapter. We have like 5 or 6 sections.
Yeah, that's kind of how I tried to group, is like 5 or 6 sections together that make sense. That's not too much stuff and make a test. I think after that, what do? We do 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.10. Now that looks like more, but like 3.6 and 3.7 and 3.8 are like nothing burgers. So it's really like kind of mostly like 4 sections again. And then the last one, 3.9, 3.11, 4.1, 4.2, 4.3, and then test. And then the last stuff will be just exam only, would be my plan. So again, I put some tests in here, often not just one chapter, but you're going to see here for like 2.1, 2.7, 2.8, 3.1, 3.2, these all really make a lot of sense that these are grouped together.
Yeah, they're all like derivative.
Yeah, 3.1 and 3.2 are just going to be like direct, like follow directly from what we did in 2.7, 2.8, or 2.1, 2.7, 2.8. They're going to fit all together really nicely into a nice little package. So it'll make sense when you see everything together. I tried to arrange things so it's like, you know, and even here, like I skipped 3.9 to put it in the next one because 3.9 is like maybe the hardest thing we do in first semester. It's either that or optimization, which is 4.7. Those are the 2 hardest things I think we do. Katie.
Are those problems we did last class?
Yes. So 2.1 would be part of Sunday's problem set, the 4 or 5 problems, whatever it was. Shouldn't have been too bad, right? That's fine. Cool. And this one would be part of Sunday's problem set also, because we'll have a chance to talk about it on Thursday. Everybody's cool? We got done so quick. I took so long to do this in second hour.
Did it last class?
I only finished like 10 minutes. Here I have like a half an hour. I don't know how I did it so much faster. You guys tend to ask just as many questions, so it's not that. I think I just must have done a better job. I did change some of the ways I said things based on the questions that second hour asked. So maybe that was it.
Maybe we just watched the video.
Oh, maybe.
But we're just like all really tired. Like,
Or you're just like, or I'm over today already. That's fair. Sure.